In this video, I'd like to go over the first confidence interval calculation section, and that is with calculating and estimating the population proportion. So first we want to go back and talk about the central limit theorem. What is the central limit theorem and what does it tell us about the sample proportion? Well, if you remember and you look back to section 6.4 with the sampling distributions, we found that if we have a particular population that we continually take samples from of the same size, and we make a distribution of all the sample proportions. So we have a population, and I believe the example in the book is they considered rolling a die 5 times, looking at the proportion of odd numbers, and then putting that itself in its own distribution. And what they found is if you look at all the sample proportions, the sample proportions are going to be a good estimate for the population proportion. So let me write that. P hat, which is our estimator. This is the sample proportion. Sample proportions, and these values, if we find a sample proportion, we're going to use that as an estimator for P, which is the population proportion. Now there are some ideas here about the central limit theorem and what it tells us about the sample proportion. The central limit theorem, we know, connects this idea of a population and a sample. And can we look at a sample and use that to predict or infer about a population? So there are some requirements that I would recommend going into section 7.2 and reading over when it comes to the sample proportions. However, I'm not going to give you a problem associated with a confidence interval with proportions where they're not going to meet the requirements. So you should definitely read over the requirements from section 7.2, but I'm not going to give you an example just so you're aware of that. So we're going to use the sample proportion, which is P hat, sample proportion, and then we're going to add and subtract what's called a margin of error. It gives us some leeway here. Margin of error. And that's going to give us an interval. So if you think back at the examples that we did up above, when we were calculating or finding an interval 2 times the standard deviation, that was considered our margin of error. So in the free throw shooting example, we were adding and subtracting 2 standard deviations worth. That was giving us a margin, giving us some room to make a mistake. And we were 95, we knew that 95% of the data was going to fall within that margin of error. So what we need to do is to take our P hat, our sample proportion, and we're going to calculate a margin of error. And we're going to add and subtract this margin of error, and that's going to give us our, and let me rewrite this. This is a P hat. We're going to add and subtract, there we go, this E, which is the margin of error. And this is going to give us our confidence interval. So how do we calculate the margin of error? Well, when we are calculating the margin of error associated with a population, we're estimating a population proportion. The first thing we need to consider is how confident do we want to be? Do we want to be 95% confident, 90% confident? Notice up above, we were doing the basketball example, we are multiplying by 2, all right, because that's very close to 1.96. We could have multiplied by 2.5 and we would have been even more confident. Or we could have multiplied by 1.2 standard deviations. We would have been less confident. So the first thing we want to do is to consider our alpha, which our alpha is the level of significance. So if we want to say, let's say we want to be 10%, alpha is equal to, let's guess here, this is just one example. If we say alpha is equal to 0.10, this is associated with a 90% confidence interval, which means we would have 5% in each tail. So the first thing we got to consider is our level of significance, and it can be 0.10, it could be 0.15, it could be lots of things. I mean, you can have a confidence interval for 70% if you want. But when we consider that level of alpha, we're then going to split that level of alpha in half. And then we want to find the z-score associated with having that alpha in half. We want to find the z-score associated with that level of confidence in half, or that level of significance in the tail. So we're going to find the z-score associated with a particular area in each tail, and then we're going to multiply this by, well, up above we used the standard deviation when we did the binomial distribution problem, but now for the proportion, this one's going to be a little bit different. It's going to be p hat, the square root of p hat times q hat, which is just 1 minus p hat, all over n. So this is going to be the formula for the margin of error that we're going to add to the population proportion and subtract. So let's go down here and look at an example. 2,518 people were randomly sampled and asked about their driving. 1,083 people said that they have honked to annoy another driver. This is just a sample, right? This is not everybody who drives, just a sample. I would recommend going over the requirements, and if you watch the mini-tab video that I go over this example with, I mention the requirements in that as well. But I do want to say that the requirements are met for us to use the confidence interval. We can create a confidence interval. Let's first find the sample proportion, because this is what is going to be in the middle, right? We're going to be starting with the sample proportion and then adding and subtracting the margin of error. So what is the sample proportion? Well, if we consider p hat is going to be, well, what's the proportion of people who said that they have honked? Well, that's 1,083 divided by 2,518. And we're going to round this to, let's say, the hundredths place. So if we were to put this on our calculators, we would get, rounding to the hundredths place, we're going to get 0.43. So this p hat, 0.43, we can kind of consider this as 43%, but we're leaving it as a proportion, so it's going to be between 0 and 1. We would say a proportion of 0.43 of people sampled said that they have honked their horn to annoy another driver. So what are we going to add and subtract from this? Well, we're going to add and subtract the margin of error. So let's find a 90% confidence interval. That's going to be important. We're going to find the margin of error associated with a 90% confidence interval. So I know if I'm talking about 90% in the middle, all right, 90% is telling me that my level of significance is 0.01. All right, 90% is associated with 10% outside of that interval. So 10% is a level of significance of 0.10. This is the probability of making an error. This is the probability that, or the area that lies outside of this interval. So if our alpha is 0.10, alpha over 2 is going to be 0.10 split in half is going to be 0.05. So that means if we're looking at 90%, there's going to be 0.05 in each tail. And if you consider a z-score associated with 0.05 with the area to the left or to the right, excuse me, in this case it's to the right, we know that that's 1.645. And that's going to be a number that you will use quite frequently. So let's now plug this information into our margin of error formula. So we're going to have the z-score. If we want to copy this down, this is the formula that we're going to bring down here. I'm going to start plugging things in. So our our critical value, z alpha over 2, 1.645, and we chose that because we want to make sure that we are multiplying so that we are going away. So here's the mean in the middle, or the population proportion, the sample proportion. We want to multiply by a certain z-score to both sides, so we get 90% in the middle. Well, 1.645 is that. That's what's going to allow us to get the 90% in the middle. So we're going to 1.645, we're going to multiply that by the square root of p hat, this is our estimator, 0.43, times q hat. Well, q hat's just going to be 1 minus 0.43. So q hat is going to be 1 minus 0.43, which is 0.57. And we're going to divide that by the number of people in our sample. All right, n. N is the number of people in our sample. That's 2,518. So what I'm going to do is put this into my calculator. Now you should be able to put this whole thing in your calculator. When you're doing that, you got to be careful. I'm going to put 1.645 times, and then I'm going to put the square root, making sure that I have parentheses, 0.43, times 0.57 divided by 2,518 end parentheses. And when you do that, I'm going to actually write this out to the thousandths place. I'm going to write this out to the thousandths place. You should get 0.016. So this is going to be approximate, 0.016. This is the value that we're going to add and subtract to our estimator here. So let's find the 90% confidence interval and interpret. Well, if you consider p hat plus the margin of error, we would get 0.43 plus 0.016. And then if you take p hat, our estimator, and subtract that margin of error, 0.43 minus 0.016, we're going to get the upper and lower bound. So 0.43 plus 0.016 and 0.43 minus 0.016. You get the upper bound being 0.446 and the lower bound being 0.414. What this is telling us is we have a certain level of confidence. Whoops, I should not have put. Oh, I accidentally erased this. Let me rewrite this. P446, 414. We know that there's a certain level of confidence that the true population proportion, not p hat, but the true population proportion, is going to be within this interval, 0.414 up to 0.446. And we obviously have a little bit of a rounding error here. But how would we interpret this? You would say we have 90% confidence that the true population proportion is between 0.414 and 0.446. It's not that there's a 90% chance or that there's a 90%, yeah, that's exactly right. There's not a 90% chance that it's contained in here, but we're 90% confident. It's a little bit different, and I can elaborate on that, and the book definitely elaborates on that. This is just one sample that we're using. It would kind of get into the percent chance if we were to continually do this over and over and over again. Right? So we have 90% confidence that the true population proportion is contained within this interval. So now let's do this whole thing here. Let's find a 95% confidence interval. If you want to pause the video here and try it, you're welcome to, but I'm going to go ahead and start it. I know that to find a 95% confidence interval, I'm going to take the margin of error, and I'm going to add that and subtract that from the population. I keep messing that up. The sample proportion, the estimator. So I need to find this margin of error. That's going to be different for this problem. We have z of, in this case, alpha over 2. I'm just going to write the formula again. Alpha over 2 times the square root of p hat times q hat all over n. What's different now is our alpha level is not 0.10 like it was before. Our alpha level is 0.05. How are we getting that? 1 minus 0.95, right? Our level of significance, if we want to be 95% confident, that means our level of significance is going to be 0.05. What is lying outside of this interval? Well, 5% is. So 0.05 is our alpha level, which means if we split that in half, because we're going to have half in each tail, when we divide 0.05 by 2, we get 0.025. And when we look up the z-score associated with 0.025, you're going to get 1.96. So let's plug these values in. The margin of error will equal 1.96 times the square root of p hat, same as it was before, 0.43. And we're going to multiply that by 0.57. And we're going to divide that by our sample size. So what is the margin of error? We're going to round this again. We're going to round this to the, let me just put this in here, 1.96. Everything else is exactly the same. And I'm going to round this to the thousandths place. I got 0.019, so it's a little bit larger. So now when I take my sample proportion and I add the margin of error, and when I take this sample proportion and I subtract the margin of error, what am I going to get? Well, 0.43 plus 0.019. Not again. There we go. And 0.43 minus 0.019. We're going to get our upper and lower bound. So you should get 0.449 and 0.411. So what would we say? How do we interpret this? We are 95% confident that the true population proportion will be contained within the interval of 0.411 and 0.449. This is calculating using the margin of error formula, but we could also use Minitab, which I can show you in another video.